So the next part, which is also the last part of this chapter 3, is about scattering of particles. Okay. So for this part of the chapter, um, I may also give you a homework problem, but this part of the chapter won't be included in your exam. Okay. So one note here is that if you look at your textbook, the topic of scattering of particles is not in the chapter of central force motion. Okay, it's in another chapter. But essentially, the physics that we are going to talk about is very closely related to the central force motion. So scattering, okay, so one famous example that you might have at least heard about is the Woodstock particle scattering experiment. Right? So I won't go into the details of this experiment itself, but essentially the physics of this experiment is about scattering. Right? So essentially what we have is that we have a source of alpha particles. Okay, alpha particles is positively charged, right? Alpha particles, and then what we have is that we shoot a beam of alpha particles, right, to the gold foil over here, just like this. So just like this, and alpha particles going to this gold foil. And if we look at this microscopically, by zooming into this gold foil, right, so we see many of the gold atoms. And this gold atom, each gold atom, of course, will have this as a nucleus. And the nucleus, right, so is again a positive charged particle. So then it will have this Coulomb potential, right? So that is a central force field. Right? So the incoming alpha particles, right, so which are also positively charged, well, of course, will be repelled by the positively charged nucleus. So you can see that I have many lines representing the alpha particles, the incoming alpha particles, right, so at different positions. So due to the repulsion, right, so the alpha particles will get deflected like this, like all these lines. And you can see that different alpha particles will be deflected differently, right? So it really depends on the initial, right, the position of the alpha particle. So what we want to study is this process, right? So this particle getting essentially getting deflected by this central force field, right? Is the process of particle scattering. So we want to be able to calculate, to given some initial conditions, how it is deflected. So then let me just give a more clean picture here. Right? So is that we have a central force field. So as shown in the picture, and then we have an incoming particle, right? So given an initial velocity v0. So we have to assume that just make things clear and simple. We assume that initially the particle is very, very far away. So almost like infinitely far away from the central force field, from the center of the central force field. So such that initially we can just assume that the potential energy of the particle is zero. So and there's one more parameter we need to specify. Okay, so that is the lateral distance between the center of the force field and the initial position of the particle. So that is this is the lateral distance. I call this T. Right. So what happens is that as it flies towards the central force field. Okay, so one thing being different here compared to the Wiggle experiment is that now I'm having this attractive central force field. Okay, so and I'll also consider the case of repulsive central force field. Okay, but let me talk about the attractive central force field first. So as the particle goes in, right, so goes like this. So now it's getting closer and closer to this central force field. That means it will get attracted. So that's why the direction of this particle will change. And you could imagine that the trajectory might look something like this. So now, so the particle will keep going, right? So essentially, after it passes over the central force field, it will just move away until it gets to infinite distance again. So just like this situation over here. So let me draw the trajectory one more time. So now assume that the particle has reached infinity again, and I call the final velocity as v1. Okay. So then the key question, right, so for this chapter is that I give you the initial condition of the particle, okay, which is v0. Well, actually not just v0, but also this p, right? So what is the final velocity v1? So that's the central problem that we are trying to answer. So here I draw the entire picture again. So first of all, right, so even without detailed calculation, we know that the magnitude of V0 and the magnitude of V1 has to be the same. Right? So because in both cases, the particle is at infinite distance away from the central force field. Right? So that means that the potential energy are zero in both cases. And by conservation of energy, the magnitude of V0 has to be the same as the magnitude of V1. And the other thing is that we know that this is the central force problem. And if we consider more specifically, right, so again, the 1 over r squared. So for 1 over r squared, we know that no matter what, the orbit only has 4 possibilities, right? So 4 kinds of orbits: parabola, parabola, ellipse, and circle. So in this case, we know that the trajectory of the particle is a hyperbola because we are having a positive energy, right? So because initially the particle has zero potential energy and it has some finite kinetic energy. So therefore, the total energy of this particle is always greater than zero. Therefore, the trajectory must be a hyperbole. Remember the last slide. So I draw the trajectory looks something like this. So then this green curve over here doesn't look like the usual hyperbola that you are thinking of, right? So if you look at the plot on the right, right? So this is the equation for the hyperbola, where the given that its eccentricity epsilon is greater than 1. The blue one is the one that you are familiar with, right? So the blue dash curve is a hyperbola that you have seen in part 1 of this chapter. And that is the case when this theta naught is 0. So remember that in part 1, so I always consider the case that theta naught is 0. But I did also mention that in general, right, so this is the form of the hyperbola or other curve, but the theta naught not necessarily equal 0. But the theta naught, the geometric meaning of this theta naught is a rotation angle of the curve, right? So here you can see that I'm drawing a red curve over here. Okay. So this red curve and this blue dash curve, they have the exact same shape actually, but the red one is rotated. That is, if you rotate the blue dash curve about the origin point by theta naught, so in this case 1.21 radians, then you will get to this red curve. You rotate this curve, just imagine that you're doing something like this for this blue curve, then you will get to the red curve. So this red curve over here looks more like the trajectory that we are talking about over here. Right. So now you can see that so the velocity vector of the particle, okay, so it's always has to be always tangential to my parabolic curve. So that is to say, if I'm able to find the shape and the orientation of the hyperbolic trajectory, then the direction of the V1 can be obtained. So now let's also talk about the repulsive case. So the repulsive case, okay, before doing any calculation, right, we know that this time as the particle comes in, it won't bend towards the direction of the central force field. Instead, it will be repelled like this. Right, so then this is roughly the shape of the trajectory that you expect. Right. So now what is this shape? Right. So it turns out that this shape is also a hyperbola. And mathematically, I will explain why in a minute. And again, right, so this hyperbola, okay, so the orientation is something that is not so familiar to you. Right? So and then again, I thought you can see the plot on the right hand side. Right? So again, the blue one would be the hyperbole that you are more familiar with. Right? So and then the red one is the one that looks like what we want over here. Okay, so let's prove. Okay, so mathematically, how we have also a hyperbola, right, for the repulsive central force field. So for in part one of the chapter, right, so we know that for this attractive central force field, we use this integral to get to the result like this. Right. So and again, also write down the alpha and the epsilon. So now if I'm talking about repulsive case, so all I need to do is to take this attractive central force and put this K to be negative, right? So when we talk about the attractive central force, we assume that this K is positive, right? So now if we just make this K to be a negative number, then we are describing repulsive central force, right? So then because now we have minus K, and it's a plus K. So then basically you will just need to, you are just doing the same integral, but all the K will have to be negative. So then because of that, the result of this integral will also be the same. It will also be this one. But what is being different is the alpha. You see that alpha contains K, right? So initially, so originally, when we talk about attractive force, this alpha would be positive. But because of the fact that this alpha is negative, then K will also, this K is negative, then alpha is also negative. However, the epsilon is unaffected because I have this K square here. So it doesn't matter whether K is positive or negative. So that is to say, for attractive force, right, so this is repulsive force. This is also obvious. Right, but here we know that for this case, alpha is equal to 0, and here alpha is smaller than 0. So then if we plot them, so what is the difference? Okay, first of all, please note that in this slide there's mistake. So first this is the plus sign. Okay. And also the for this plot, orientation is wrong. Okay, so let me just simply redraw the plot over here. So it should be looking like this. So the two curves should be on the right hand side of this origin point. Okay, instead of left hand side. So, and this part, let me just label it first. Okay, so this is the correct plot. So here, I want to mention one thing is that when I write down this equation here, you can actually see that R is sometimes positive and sometimes negative. Okay. So let's consider the case, first of all, consider the case where alpha is greater than 0. So this plot over here. And if alpha is greater than 0, then if I want positive R, so that means that the denominator also has to be positive. But sometimes the denominator is actually negative. So I can draw a picture for the factor in the denominator. So in these two pictures, okay, just for simplicity, the theta naught. So that in that case, if I want to plot this curve, what would I get? I would get curve that looks like this. So this is 1 plus epsilon. This is 1 minus epsilon. So you can see that over this range and this range, this epsilon cosine theta plus 1 is positive. Otherwise, it's negative. Right. So in our physical problem, so we only plot the physical result, which is the case when R is greater than 0. So that's why in the part 1 of this chapter, so you see that we only plot this solid red line. But for hyperbola, you know that it's actually a pair. So the other curve of this hyperbola is actually this dashed curve over here. And this dashed curve actually corresponds to the negative R result. So what it means is that, so let me try to, so for any point on the hyperbola, so that is the coordinate R theta. And R, this distance, and then this is the theta. So as you get to larger and larger data, right? So then that means you get to here, over there, and until r equals infinity, you still have some finite value of data, right? So suppose one, but you still have some data value. So in that case, what you have, right, would still be some positive r, right? So that tends to infinity, right? So that would be the case when this denominator really close to zero. So once but when I draw all this data over here, I'm still within this range. Okay. And similarly, so if I'm over here or here, right? So the theta angle, right? So if I'm over here, then the theta I have this one. So, and for that case, I'm within this range over here. So I still get the r greater than 0. So now, if my theta, so now, okay, my origin point over here. Now, if I select a theta value, which is this one, okay. So suppose this theta value is a value such that this denominator is negative. That is, theta now is somewhere here. So then what happens is that I have a negative value of r. Right. So everything over this side would be a positive r. But this equation does not give any value of positive r. So it gives negative value of r. So what it means is that this line has to flip over to here. Okay. And that's how I get to this point. It's a negative value of r over here. This side represents positive value of r. Positive r, negative. Right, and that's why I have this point. And this is a point on this dashed curve. Okay. So now if I look at the other case, okay, so the repulsive case. Okay. What happened is that now if I want positive value of r, this time I do want the denominator to be negative in order to get positive value of r, right? Because alpha this time is negative. So I want a negative number divided by another negative number to get a positive. So that's why this time I want this range of the theta would give me a positive R result. Okay. And I think okay, I put the typo here. This one greater than 0. This is smaller than 0. So in both cases, so R greater than 0 is the part that we care about. It's the physical result. So the R smaller than 0 is a non-physical result that we don't actually draw out. Right, so now you can see for the attractive case, right, so this solid line is the physical result, and it makes sense, right? So because the particle tends to attracted by this point, so that's why I have this curve over here. So similarly, right, so on the other hand, for this case, repulsive case, right, so this is the physical part of the result. Right, so you do expect something like this. Right, so trajectory, the particle looks like it's getting repelled by this center. Right. This part is not physical because you don't expect a particle that goes like this when you have this repulsive force. Okay, so here, if you don't fully understand, okay, so that is still okay, right? So all you need to really know is that in both attractive and repulsive force, the curve is hyperbolic. So now let's get back to our original goal, right? So our original goal is that we want to find out V1, right? So given this V0 and this B. So here, let me actually set up the problems and all the variables, okay? So on the left-hand side, I do have the repulsive case, and on the right-hand side, I do have the attractive case. So let me just focus on the one on the left first. Okay. So I have, again, right, so this incoming particle with this initial velocity V0, and after the scattering, I have the final velocity V1. And I have this dashed line over here, and this dashed line over here. And these two dashed lines are the two asymptotic lines for the hyperbola, right? So as you go to infinity, right, so this hyperbola looks like a straight line. Right? So, and this dashed line is that asymptotic line. Okay, similarly, this is the asymptotic line for the other side. So the B is the lateral distance that I mentioned earlier, right? Is this one. This is the B. So and I call the B as the so-called impact parameter. So the scattering angle is over here, phi prime, which is the angle between this horizontal dashed line and this asymptotic dashed line, phi prime. Right, so because this is the phi prime tells you the angle between the initial velocity and the final velocity. So now I have these two angles here, which I call theta max, right? So theta max is the angle between the two asymptotic lines and this OP. Okay, so what is the P? I forgot to mention P. So P is the point of minimum distance between this scattering center O and the trajectory. Right, so you can see, right, so here the distance is that much, right, so here the distance is that much, right, so any point would have longer distance compared to this point over here. Okay, so what is the data max? Right, so first of all, you see that this dashed line is just obtained by shifting this dashed line down. And this dashed line is just obtained by shifting this dashed line down. Right, so that's why this is data max. Right, so this is also data max. So this is also data max. So I'm not going to repeat everything for the case of the attractive force, but I think the plot is the figure is also quite self-explanatory. And as I said, right, so the difference is that for the case of attractive force, the hyperbole would be bent to the other side, right? Because the attraction, but the repulsion, I will bend it up, attraction bend down. So and let so the initial angular momentum of the particle can be calculated by using so this formula. So the angular momentum of our point O is mv naught times this lateral distance d. And this is a conserved quantity because we have central force. So now I want to find out the orientation and the shape of the hyperbola. Right? So as I said in the beginning,